Okay, welcome and to this session on computational tools in materials technology. My name is Guru Rajan. I'm from the Department of Metallurgical Engineering and Material Science at Indian Institute of Technology, Bombay. The teaching assistant for this course is Shobhan Ray, and both of us have put together some material we will go through, and there will be small tutorials and assignments towards the end of the course. So this is the preliminary section. In this section, I'm going to give a short introduction to computational methods that we will be using. And before we actually go do any computational calculations, we also have to know about how numerical computation is done and what are the types of errors that occurs in this sort of computation. So we will discuss that first. So in this module, we are going to use computers for solving problems. And the problems are of interest to material scientists and engineers. So that is how this has been put together. But the methods that we use for solving these problems, they are well known and they are discussed in many engineering mathematics courses under the topic of numerical methods. So the methods themselves are very well known, but we will choose problems that are of specific interest to material science and engineering. So the problems are chosen and they are chosen for illustration of these methods, and they are chosen for material science and engineering. Okay, so it's a pity that we don't have access to computers in this course. Ideally, when I teach this course here at IIT Bombay, every student gets a computer in which they sit, and then when we do the discussion of the method or problems, the students are asked to solve by themselves. So on the computer, they try to solve it themselves, and we run lots of hands-on tutorial sessions like that. So it's really not a lecture-based course, and it is done more in the tutorial fashion. And so they are best learnt if you can use a computer and program the algorithms in the computer and do it by yourself. One more advantage is there in using computers because we have programs which will help us plot and graphically represent the results. Okay. And such graphical representation helps us understand the problems, understand the solution methodology, understand the way in which the solution is obtained, understand the structure of these methods or algorithms, and so on and so forth. So it's really useful to do all these things using a computer. But unfortunately in this course we don't have access to a computer throughout these sessions. So instead what we are going to do is that we will try to do as many of these computations whichever is possible to do using a small calculator or a small scientific calculator with which you can do. So that is what we will try. So some of the methods I have chosen and some of the problems I have chosen in such a way that they are ideal for doing by hand. Okay, so once you understand, there is also enough material about these methodologies, some of which has been uploaded by me as part of an NPTEL course. So I will send a link towards the end of this course. So you can actually go take a look at those scripts, and you can try to use them on your computers and try to have a better understanding of the methods, as well as solving problems which are really complicated, which require a computer for you to solve the problems. Okay. So we will do that towards the end of this course. Okay. So so the supplementary material uses a program called the GNU Octave. GNU Octave is open source replacement for MATLAB. So MATLAB is a commercial software, so sometimes you have to pay to have access to MATLAB, but Octave is free, and you can download and load Octave both on Linux machines and Windows machines. So it helps you to have Octave, and it's free, so you can download, and then you can use the scripts that that we have written to play with, and then you can also try to solve your own problems and improve on them, and so on and so forth. Okay. The best thing that I like about GNU Octave is that there is lots of graphic visualization, and many a times visualization actually helps us understand the method and the algorithms. So it's really nice to have such a graphical interface when we are doing the computation. Okay. So first thing that we need to know is that when we are doing computation, we are using the computer to do calculations. These are different from the calculations that we would do using pen and paper. So pen and paper calculations are very accurate. Okay, there is no approximation that is involved. On the other hand, in computers, because they use only a limited number of binary digits to store numbers, the representation of numbers itself is approximate. Because of which the calculations carried out in computers is approximate. Okay. So this is a very, very basic difference between doing computations by hand and doing computations by computers. So we always have to worry about the accuracy with which we are representing the numbers and whether that will interfere with the method that we are using. Because if it interferes, then the method will not give solution. So using pen and paper, you might be able to get answers, but for the same method, if you use computers, probably you will not get answers or you will get wrong answers. So this is a concern. That is why before we start any numerical method or any numerical algorithm in these kind of courses, we first talk about what are the types of errors and how they affect and how to calculate and so on and so forth before we actually start doing the computations. Okay, so on a computer, a typical representation of a real number, for example, if you are doing the computation in single precision, then typically about 32 binary digits or bits are used to store the number. And if you are using double precision, it's called double because typically it is double the size of single precision. Number of bits used to store is twice as much as single precision. So if single precision is 32, double precision will be 64 bits to store the real numbers. If you have single and double precision, typically that also means that the accuracy of numbers represented by them is of the order of 10 power minus 8 or 10 power minus 60. This is known as machine accuracy. That is numbers which are smaller than 10 power minus 8 or 10 power minus 16 cannot be represented on the computer. The computer thinks of those numbers as the same. You know, if you have two numbers which are smaller than 10 power minus 16, it cannot distinguish between them. And most of the scientific computation actually requires double precision. Okay, otherwise you will lose lots of precision and accuracy when you are doing the calculation. So most of the times when you use computers, we typically use double precision calculations for doing scientific computation. So there is the question of precision and there is a question of range. Precision is what places restrictions on the smallest and the largest number that can be represented on computers. Okay. Any number smaller than or larger than some number leads to an underflow or overflow. That is, those numbers cannot be represented completely. Integers are also restricted in range, that is, there is a small number and there is a large number beyond which you cannot represent numbers, but there is no problem of accuracy associated with their representation. So both for integers and real numbers on computers there is a range. Beyond that range you can't represent numbers. But in the case of real numbers, even within that range when you represent, there are some small numbers which you cannot represent on computers correctly because there is a precision that is associated with the machine because of the way it represents the numbers on the machine using binary digits. Okay. So there are many different types of errors that one comes across when one is doing numerical computation. One of the errors is known as round-off errors. So round-off errors are basically accumulation of errors due to any arithmetic operation on real numbers. So you have real numbers, they are only represented approximately. Then you carry out some arithmetic operation on those numbers, then that will also be only approximate, but because of the basic approximation of the numbers themselves, the errors might keep accumulating. Okay. So and this is known as round-off error. This comes because simply beyond some digits the numbers are discarded. Okay, up to some decimal position only can be stored and represented on the computer. Beyond that position, everything is discarded. So the error associated, if suppose you do n arithmetic operations, okay, on a machine which has an accuracy of epsilon m, that is the machine accuracy. Typically, you would assume that this rounding of error, if it is random, for example, then it is square root n times epsilon m. That is the total error that you would accumulate if you do n computations. However, most of the times the error cannot be assumed to be random. The methodology that you use, the algorithm that you use, or the calculations that you do, they bring their own regularities, and that means the error is going to grow in a very ordered fashion. I mean, it's not random. Random errors means sometimes they might cancel out each other. Some error might be positive, some error might be negative, so they will cancel out each other. But that kind of cancellation does not happen in many of the algorithms. Okay. So the error, if you do n computations on a machine with accuracy epsilon m, the error goes as n times epsilon. Okay. So while carrying out numerical computations, you have to keep in mind the round off error. So you have to always worry about how much is the round off error going to accumulate to, especially if you are using very large number of arithmetic operations in your computations. There are the second type of errors which are known as truncation errors. Okay. Truncation errors are basically errors associated with approximations used in the numerical algorithm. For example, if you want to calculate sin x, then you can calculate it to different accuracies by summing in a series. So the series goes as x minus x cube by 3 factorial plus x power 5 by 5 factorial minus x 7 by 7 factorial and so on. So what we do is that if you want to calculate sin x for a particular x, then we decide up to what order in this series we will sum. So depending on where you stop the summation, you will get errors. So these are known as truncation errors because you are truncating the series beyond some point. So the errors associated with such truncation is known as truncation error. And so truncation errors are there everywhere. Even if I do with pen and paper, because I am going to truncate at some point, I will get truncation errors. Okay. So in most of the numerical methods, the algorithms are devised in such a way that they will minimize the truncation errors as much as possible. So if with the same number of computations, you can get a better accuracy or a lesser truncation error. That is what you will try to do. So this is how we actually develop numerical methods and improve them. But these are, so there is round off error that is specific to computers, the way numbers are stored in them. There is truncation error which is there in any case. Even if you do pen and paper calculation, you will get truncation errors when you do pen and paper calculation. Then when we are using numerical methods, we are always worried about the stability of the algorithm. So in an algorithm, for some reason, if truncation errors interact with rounding of errors and lead to magnification of errors, and that can lead to complete breakdown of the calculations themselves, then such a method is known as unstable method. So the idea is to make use of methods which are as stable as possible. Okay. So stability is something that we have to be worried about, and stability issues come about because the two types of errors that we have. We try to do certain calculations to certain approximations, but we are also trying to do it with numbers themselves which are represented in an approximate manner. So these two approximations should not reinforce each other and hence grow and lead to an unstable or breakdown in calculations. So then we have difficulty. So stability is a problem about which we are most of the times worried when we are doing numerical computations. So it's always a good idea because we know that there are going to be errors, and these errors are going to grow or sometimes they might cancel out. So we want to know how the error is behaving, and when we are doing numerical computation, we will be closely monitoring what is happening to errors. Okay, so there are error bounds and there are also ways in which error propagates in computations, both of which we want to understand. So there are two types of bounds that can be placed on errors. One is the error bound, the other one is the relative error bound. Okay. Suppose you have an actual quantity that is A, and the approximate value that you have obtained for this quantity is A tilde. Now the error bound then is defined as some a minus a tilde, the modulus of this, that is less than or equal to some beta. Now the relative error bound is basically taking the error bound and dividing by the actual quantity value. Okay, so beta r is nothing but less than or equal to a minus a tilde, the modulus, divided by a itself. Okay. Now if you do addition and subtraction operations, the error bound for the results is the sum of the error bounds for the terms. In multiplication and division, the error bound for the relative errors for the results is approximately the sum of the error bounds for the relative errors of the given terms. Okay. So we have error bound, and that is relevant for addition and subtraction. We have relative error bound, and relative error bounds is relevant for multiplication and division. In the case of addition and subtraction, error bound for the result is basically sum of the error bound for the terms. On the other hand, for multiplication and division, the relative error bound is approximately the sum of the error bounds. Okay, so it's not exactly the sum. So approximately that is the sum. Okay. So when you do any calculation, of course, it's always a good idea to estimate the error. But the error bound and relative error that we have defined already assume that we know the actual answer. So many times we don't know the actual answer, but we still want to have an handle on the error. How much is it is something that we would like to understand. Okay. So it's always a good idea to estimate the error. The way to do an error estimation is that many of these algorithms come with their own accuracies or convergence criterion or some criterion for stopping the computation or stopping the iterations and so on and so forth. So those basically determine to what accuracy you are calculating the answer. One way to have an handle on error is that you do the calculation with some accuracy or some convergence criterion or with some criterion for stopping the computation. And then you do another computation, but this time slightly higher convergence criterion, I mean slightly more stricter convergence criterion, slightly lower value of error and so on and so forth. And you compare the results that you get at the end of these two computations, and that to a large extent tells you about the kind of errors that you are making in your computation. Sometimes the algorithm itself is devised in such a way that you will keep looking at the errors and you will stop it when these two different consecutive computations with different accuracies actually leads to quite close values for your answer. Okay, so this is a practical way of doing an error estimate, and it's very important. One more thing which is very important, which we will have a chance to use a lot in general. I mean, it has nothing to do with numerical computation. If you are an engineer, probably it is something that you should know, which is the Taylor series expansion. Okay, and Taylor series expansion is used extensively. And some of the very important numerical algorithms use Taylor series as a starting point. So just to recall, if you have f which is a function of some x, then f of x plus or minus h is basically given by doing an expansion, and that is f at the point x itself plus or minus the h, that is the point at which you are trying to compute the function value, which is away from x, times the slope of the f of x curve, so f prime of x plus the higher order correction. So the first is the slope correction, second one is the kind of acceleration or curvature kind of correction, third one is the aberration kind of correction. So it's h squared by 2 factorial f double prime of x plus or minus h cube by 3 factorial f triple prime of x and so on and so forth. Okay, where the prime actually differentiates, denotes differentiation with respect to x for that point. So the f prime is dou f by dou x, f double prime is d squared f by dx squared and so on and so forth. So Taylor series expansion is also something we will have a chance to use some of this later in our computations today. So it's just to remind you that I'm assuming that you have seen Taylor series expansion and you are comfortable with it. This is just to remind you. So this brings us towards the end of the preliminaries as far as numerical computations are concerned. And before we end, I want you to do a small computation for me. And it's a very trivial computation. We have a quadratic equation, x squared minus 100.001x plus 0.1 is equal to 0. Okay, so this is the equation. You know that the roots for this equation can be estimated using the formula x is equal to 1 by 2a, and that multiplies minus b plus or minus square root of b squared minus 4ac. So this is one way of calculating the answer. There is also another way of finding out the roots. So the first one is use the formula for one of the roots, that is x1 is 1 by 2a multiplying minus b plus square root of b squared minus 4ac. For the second root, instead of subtracting the square root of b squared minus 4ac from minus b, what we do is that we use the properties of these roots because the x2 should be x1, x2 should be equal to c by a. So where x1, x2 are the two roots. So you can calculate x2 by just knowing the c value, a value and the first root value. So x2 is c by ax1. So this is the way of calculating two roots. These the two methods are acceptable and are the same at some level. They are not different. But if you do computation on a calculator, then there is an interesting difference from the values that you obtain using these two methodologies. Especially if you can make your calculator do computation, say only up to some accuracy, say 4 or 6 decimal points. Up to that accuracy, if you try to do calculation, then you will find something interesting. So I would like you to do these two computations using a calculator, if possible only by keeping the accuracy to 10 power minus 6 or so, and I want you to tell me the answer. Okay. So then we will have a discussion on the numbers that you find before we proceed to the next. Okay. So did you find the answer? Can you give it to me? So you can give it to me in chat mode or 100 and 0.001. Okay, I see one answer, 100 and 0.001. That is the right answer, but do you get the same number 100 and 0.001 using both the methods, or do you get different using the two different methods? Got same values? Okay. So I have my TA here, Shobhan. Did you get same method, same values using both the methods? Yes. Okay. So Shobhan says that he also got the same numbers using both the methods, but if you so your calculator must be doing to a higher accuracy the computations. But for example, when I did this computation on my computer, where I can look at much higher accuracy. So the computer gives me numbers. For example, it doesn't give me 0.001 for the second root. It gives me 0.000999999, etc. So it goes up to some 15, 16 digits like that, and then there is some 7 or 8. Now, if that number is reported to an accuracy like 3 or 4, then all those 9 will be converted to 1 in the third decimal place, because from fourth decimal place on it is putting 999. Okay. That happens because if you look at the two roots, the difference between minus b and square root of b squared minus 4ac, that is 0.001. So that is the b number and the square root of b squared minus 4ac, they are quite close. That is the reason why the difference gives such. So you are taking two numbers which are quite close to each other and you are trying to subtract one from the other, and in this case the numerical errors are large. On the other hand, when you use the other formula, x2 is c by ax1, there is no such problem, so you get the same number. Okay, so it's good that you got both the same numbers, but sometimes on computers you might not get the same numbers, and that time the accuracy becomes an important problem. And there is another small issue related to this. So if suppose b is greater than 0, so then what happens? Then you need to calculate x2 using the formula, that is 1 by 2a minus b minus square root of b squared minus 4ac, and then the x1 has to be obtained using the second formula, c by a, x2 is x1. Okay, so it depends on which are the two numbers which are close to each other. So you should try avoiding subtracting two nearly equivalent numbers, because the errors can start showing. Okay, so it's good that you got both the methods giving you the same number, but you also have to be careful because sometimes they can give different numbers. Okay, so this is an exercise you can do. You can go to a computer or calculator which will show you numbers to a much higher accuracy. There you will see that these two numbers are actually not the same. Okay, very good. So now that we have done this, let us go to an actual numerical method. Okay, so this is known as fitting. So we will discuss in this set of modules the fitting. Okay, so what is fitting? Okay, suppose you have done some experiments. Using the experiments, you identify the change in some quantity y as a function of some parameter x. For example, you might be putting some strain and you might be measuring stress in your material. So the stress strain data then you have, and that is the data that you have obtained through experiments. Okay. Fitting is a method by which we generate an expression which connects the x to y. So how does y depend on x? That expression, if we obtained, that is known as fitting. There is also interpolation and extrapolation. So that these are also the process of finding y value for a given x value, but there is no experimental data for that particular x. So you need to take nearby x values and find out what the corresponding y values are, and using them as an indicator for some x value in between. For example, if you try to calculate what is the y value, that is known as interpolation. Sometimes you might have some x value and you might be going outside of the range of those x values to calculate for some x value which lies outside the range what the y value is, then that is known as extrapolation. So these are done typically, fitting and interpolation and extrapolation. All three are done to know the y values for some x value for which you have not done the experiment. You have some experimental data, then there are gaps in the experimental data. In those regions, if you want to get the relationship, then sometimes you can fit and then use the fitted expression to calculate. Sometimes you can just use the nearby values and try to do an interpolation or extrapolation. Now, why is this important? So in material science, there is one important law which is known as Vegard's law. Okay, this Vegard's law tells about the change in lattice parameter with composition. Okay. Specifically, Vegard's law says that with composition, the lattice parameter changes linearly in an alloy, or in a, if you take A type of atoms and if you take B type of atoms. Suppose you have pure A, it will have some lattice parameter, and if you start replacing some of the A atoms by B atoms corresponding to the composition, how much you are replacing, correspondingly the lattice parameter for the alloy AB will now increase or decrease. It depends on whether the B lattice parameter is going to be lower or higher than A lattice parameter. Okay, so this is a typical behavior. This typically happens for very small ranges of composition, but in some systems this can happen throughout the range. If uniformly the atoms of one type are replaced by another, and if it is a nicely behaved system, such uniform replacement is possible, then you will see Vegard's law is being obeyed throughout the entire composition range. That is from pure A to pure B, the lattice parameter just is a straight line with composition. So it is possible, and here is data for the silicon germanium system. Okay, so on the right hand side we have the mole percent of silicon. So that is starting from 100%, that means that is pure silicon, to 0%, that is pure germanium. Okay, the lattice parameter of pure silicon is 5.434 angstroms, and lattice parameter of pure germanium is 5.657 angstroms. So for the intermediate compositions, that is 85.8 mole percent silicon, 57.5 mole percent silicon and 22.9 mole percent silicon, the lattice parameters are known to be 5.461, 5.518 and 5.593 respectively. So this is from the data which was published sometime in 1954. And it is also known, so the lattice parameters are given, and in this table I have given some 5 data points. Actually in my NPTEL tutorial notes I have given the complete data range, so there is more data, but for our purposes when we are doing computations, let us stick to these 5 numbers. Okay, so this is the data with mole percent, varying mole percent of silicon, how the lattice parameter changes. This is the experimental data, and it is known that in the silicon germanium system Weger's law is obeyed, that is the composition and lattice parameter have a linear relationship. You keep on increasing composition, the lattice parameter will keep on increasing in mole percent of silicon, some 100% silicon to 0% silicon, that is in germanium. If you increase, the lattice parameter increases because germanium has the higher lattice parameter. So this is known. So suppose you want to find out the value of lattice parameter, let's say 50 mole percent silicon. Okay, so we know that the lattice parameter changes linearly. So we know what is the lattice parameter for 22.9 and 57.5 mole percent silicon. So we can use these 2 points. So you have x1 corresponding y1 value, you have x2 corresponding y2 value. So you can sort of have a linear interpolation, put a linear line between these 2 points, and using that you can calculate the lattice parameter for any x that lies in between these 2 values. So it is possible to do. And how do we do that? So this is the first thing that we are going to do. So first exercise is to show that the formula for a line that passes through the points x1, y1 and x2, y2 is as given. It is y equal to y2 minus y1 by x2 minus x1 times x plus y1 x2 minus y2 x1 by x2 minus x1. Okay. So I'm going to show you this computation on the. So how do we do? We know that the equation for a straight line is y equal to mx plus c. Okay. So we know that the 2 points x1, y1 actually satisfies this equation, and so also x2, y2, right? That also satisfies. What is x1? We have been given the lattice parameter, okay, and x1 is basically the mole percent silicon. Okay, so similarly we have another mole percent silicon and the corresponding lattice parameter. Okay, so these are the values that we have and we are trying to calculate. So this x1 y1 satisfies this equation. So that means y1 equal to m x1 plus c. Okay. So this also satisfies, that means y2 equal to m x2 plus c. Okay. So then we have 2 unknowns, one is m, the other one is c, right? So if we can identify what is m and what is c, then we can have the straight line expression. So then for any x value that is given, then we can calculate the y value. So that is what we are trying to do. So let us take these 2 equations and solve for the 2 unknowns. The first one is very simple. So if I subtract y2 minus y1 will be equal to m times x2 minus x1 because the c and c will get cancelled. So m is nothing but y2 minus y1 by x2 minus x1. Okay, so m we have already found, so y is equal to y2 minus y1 by x2 minus x1 times x plus c. Okay. Now what is c? We know that these expressions are valid. y1 is mx1 plus c. So for example, to calculate c, let us assume the first case when it is x1 here, it is y1. So y1 equal to y2 minus y1 by x2 minus x1 times x1 plus c. So that means c is what? y1, okay, minus y2 minus y1 into x1 by x2 minus x1. Okay, so it becomes y1 x2 minus y1 x1 minus y2 x1. Okay, and then this minus and minus is plus y1 x1 plus y1 x1 divided by x2 minus x1. Okay, so this y1 x1, this y1 x1 is going to cancel. So we have y1 x2 minus y2 x1 divided by x2 minus x1. Okay, so that is what the expression given in the slides. So we have finally identified y to be m to be y2 minus y1 by x2 minus x1, and c will be y1 x2 minus y2 x1 by x2 minus x1. So finally we have the formula, namely y equal to y2 minus y1 by x2 minus x1 times x plus y1 x2 minus y2 x1 divided by x2 minus x1. Okay, so the data that is given in the slide, you can see that x value x1 is 22.9, x2 is 57.5. Okay. What are the corresponding y values? From the table it is clear that y1 is 5.593. What is y2? That is 5.518. Okay. Now what do we want to calculate? When x is equal to 50, right? Okay. We want to know what is the y. So I want you to substitute these values. So y is equal to 5.518 minus 5.593 divided by 57.5 minus 22.9 times 50 plus 5.593 times 57.5 minus 5.518 times 22.9, this entire thing divided by 57.5 minus 22.9. So can you do this calculation and tell me what the y is? Okay, so what we are trying to do is linear interpolation. We have 2 points x1, y1, x2, y2. Using that, we tried to find out in y equal to mx plus c what the m and c values are. That's what we derived. And using those values, now we have written a linear interpolation formula. I want you to substitute the values and do the computation and tell me what is the lattice parameter at composition 50 mole % silicon. Once you get the numbers, you can tell me through the chat window. You can type in the numbers and we will see what numbers you obtain and if everybody obtains. So obviously because it's a linear interpolation, the lattice parameter should lie between the y1, y2 values, 5.593 to 5.518. and because we are looking at 50, the value that you should get to should be closer to 5.518. That is for 57.5. Okay, so it will be away from 5.59 and it will be closer to, so that is, if you can approximately, it's one is 5.6, the other one is 5.2, 5.52, so you will be closer to 5.52. So I have one answer. So I'm going to write down the answers that I'm getting on the screen here. So I have got one answer which is 5.532 5342 577. Okay, this is from PSGCT. I have got one answer. Is there any other answer? Did everybody get this or they get something else? 57 after this. 5.534257226. Okay. So I've got another number. Okay. Yeah, 572254. Okay. I'm getting a number. Somebody is giving 5.516. I'm not sure about this. Somebody is getting 5.5335. Okay. And somebody is giving 5.534257. Okay. So 53427. Okay. So this seems to be the number. Okay, as you can see, I don't know, I mean in these two cases I think the answers have to be checked. I don't think it can be off so much, but some amount of differences, this could be a transcription error, but 226 and 2254, these kind of things can happen because of numerical errors. Okay, so this and most of the calculations will get, but depending on your accuracy, you might get this number right or not. I think these needs to be checked. Okay, and 334257. Yeah, so this is okay. Okay, and for 335, because it is 42, I'm not sure why it became 5. I mean, if this is a number larger than 5, then I can understand that somebody tried to approximate it to 335. So I'm not sure about this number. This certainly seems to be problematic. So it's not clear to me what. You may have to check the algebra. But okay, so you can see that you got number, and from the number it is clear that 5.534 is closer to this 518. 553 is just quite close to this than 59, and that is because the composition is quite closer to x2 here. Okay, so yeah, so I have gotten more numbers. So everybody pretty much got 5342, 57225 or 226. Okay, so very good. So we will go back to the slides. Okay, so this is interpolation. So I had 2 points and I knew that it's a straight line, so I interpolated by a straight line between the 2 points and I got the value. Okay, now there is another problem. Okay, so one can always ask the question, how correct is the answer that we got using linear interpolation? We used linear interpolation, we got the number. For example, somebody else might have decided that the 2 points that they will choose will be the data for 22.9 and 85.8 and calculate the lattice parameter. This time, for example, you can calculate the lattice parameter for 57.5 mole percent alloy, and for which we already have the experimental data. So if you take the data for 22.9 and 85.8 and interpolate, obtain the value for 57.5, you have the experimentally reported value for 57.5. Do they compare? So you can use the same formula, and I have used the same formula, and I tried to calculate. I got 5.520 angstroms from calculation. The reported value is 5.518. Okay. So those two are quite close. Okay. So the error is in the third decimal place, 0.002. But if there is a question as to why there is a difference, then the answer is that the error is due to experimental error. Okay, so the mismatch is because of experimental errors. So when I calculate for any composition the lattice parameter, that is accurate only within some range, because of which if I take the given value to be the final value and then do an interpolation, sometimes it might be slightly off. Okay. So actually, is there a way in which we can account for the fact that experimental data is error prone and try to minimize that error as much as possible? If you ask that question, so what we did was interpolation. We just took two experimental values, we found the value for some the x value in between. So there is an answer. Yes, there is a better way to calculate the parameter y, which takes into account for the fact that the experimental data is error prone. So that allows for these experimental errors and tries to somehow mitigate the effect of these errors. And that is by using a straight line and use the fitted expression to calculate the value. So what do we mean by that? We mean the following. Okay. So we are still attempting to find the parameters m and c for the straight line y equal to mx plus c. Okay. But this time we are trying to find it out in the following fashion. Okay. So I'm going to show you again. Okay. So what we are trying to do is as follows. So I have some y, okay, which is calculated for some x. So there are some data points. Okay. I know that this data follows a straight line. So there is this is m, and wherever it intercepts, this is c. So this curve is y equal to mx plus c. Okay. Now I want to calculate what is m and what is c. But while calculating this m and c, the way I want to calculate m and c is by minimizing the distance of these experimental points from my line. Okay. So I want to minimize the distance of these points from the line as much as possible. Okay. So minimize distance from assumed line. Okay, as much as possible. Okay. This means we have a way of calculating the distance of the points from the line, and then we are going to minimize that. The way it is done is shown in the slide. Okay. So suppose if xi, yi are the experimental points and there are some n such points, then what we try to do is to minimize summation over I yi minus mxi minus c whole squared. Okay, this is known as least square fitting because we are trying to calculate m and c by minimizing this quantity. And if you look at this quantity, this is nothing but the mx plus c is the curve that I am assuming, yi is the actual point. So mxi minus c will be actually the point that I would get by putting the data into my curve. So this is the distance of the point from the assumed curve. I have squared it because sometimes some of the points, as you saw, might lie above, some of the points might lie below. If I just add the differences, they might cancel out as long as the line goes away from all the points, say equal distance from top and bottom, then that can actually become 0. So I don't want that. So the error, I mean whether it deviates above or below is still an error. So to take this into account, You can use modulus, but modulus is very difficult with reference to differentiation and things like that. So we take the square. Okay. So the square, and we are trying to minimize the square. So it is least square, and the exercise that we are trying to do is to get the M and C which fits the experimental data. So it's known as least square fitting. Okay. So this kind of curve fitting, I mean, it's linear least square fit and higher order fits are quite common. Okay. So it's a linear fit because we are trying to fit it to mx plus c. You can have a quadratic least square fit and any higher order, nth order least square fit. Least square relates to how we are defining the error, and that we are trying to minimize. Fitting is the exercise of getting these coefficients in the expression, and whether the fitting is done for a linear expression, quadratic expression, etc. tells what type of least square fit it is that we are trying to achieve. Okay. So now how this is done, not going to go into the details of the algebra. For least square fitting, if you want to fit a straight line for n data points, then M and C are obtained by solving the set of two equations. There are two unknowns, so you need two equations, and the equations are as follows. So you sum all x and you sum all y, so that makes the first equation. M times sum of all x plus n, which is the number of data points, which is 5 in our case, times c is equal to summation of all y, and m times summation of x squared plus c times summation of x is equal to summation of xy. So if you go through a textbook like Kreisig Advanced Engineering Mathematics, you will see that by writing the error and trying to do minimization on them, you can end up with these two equations. Okay. These two equations then fit a straight line in the least square sense by minimizing error in the least square sense, and when you have n data points. Okay. So the next exercise is of course to fit for Vegar's law. Okay, we have the data, and this means we need to calculate some x, some y, some x squared, some xi, yi. Okay, these are calculations which are little bit involved. Of course, you have a calculator, so it should not be very difficult to do, but algebra can take some time for you to do. Okay, so here is what I have ended up by getting by doing those summations. Okay, so the exercise for you now is to actually do this sum x, sum y, sum xi squared, sum xi yi, and get the numbers and confirm that you are getting the numbers which are shown. Okay, so 266.2 is nothing but summation of x, right, and there is 5. 27.66 is summation of y, and 21,192.3 is summation x squared. Okay, 266.2 is anyway summation x, that we know already, and 1457.3185 is basically summation xi yi. Okay, so it is a good exercise for you to check that this is indeed so. Once you have confirmed that this is indeed so, you have to solve two equations and two unknowns. Okay. So once you solve, you will get M and C. Once you have M and C, you can calculate the lattice parameter for composition x equal to 50. Okay. So this is the next exercise that I want you to do. I want you to, this you can check. The slides will be available for you, so sometime when you can sit down and check. But can you solve these equations, get the M and C values, and using that to calculate the composition for composition 50, what is the lattice parameter? Okay. Can you do that and let me know what the numbers are? You can first tell me what is the M value, you can then tell me what is the C value, then you can tell me what is the lattice parameter for a composition of 50. Okay. Okay. So I'm very happy to see answers have started coming. So M is 0.0022 is one answer, and somebody reports M to be minus 0.0022. Okay, and C is so I see different answers. So somebody is giving 5.60 and somebody is giving 5.649849. Okay, so it's interesting. So we'll take more values. So Y value is given 5.5397. Okay, so I get more minus 2.2 e power minus 3 and C as 5.6498. Okay, so somebody gave me, maybe they forgot the sign, but 6048 is not clear. Okay, so you can also tell me what is the lattice parameter value you are getting by using this fitting. Then I'll show you my calculation. I don't know, I have done probably right, or maybe I haven't, so we will take a look at. So for 50% mole percent alloy, what is the lattice parameter? We calculated that using interpolation previously. So you remember that we did it using interpolation and we got a value of 5.52 if I interpolated between 22.9 and 85.8, or 5.534 to 577, right? If I interpolated between 22.9 and 57.5. Okay, so now what is the value that we are getting in this case? We are getting 5.6498, though, that is C. 5.64984 is C. So can you give me the lattice parameter? Yes, M is, I don't know if there is a minus sign, 0.002. There is a minus sign, no? So there is a minus sign, so somebody is getting M positive, so I think there is some error there, and lattice parameter is 5.539735. Okay, so yes, so one lattice parameter I am getting, that is 5.539735. Okay, so let's go look at what is it that I got. Okay, I hope I have it in my slides. Let's take a look at it. Okay, 5.5397. Yeah, so two people have given me 5.5397. Okay, so good. So let's go take a look at it. Okay, so here are my fitting parameters, minus 0.0022023, that is the M value. So most of you got that, and 5.64985, that is the C value, that also most of you got. So if you use the formula, you get a composition of 5.523. Okay. Okay. So, but you get 5.5397 for 57.5. For 50.5. Okay, so for 57.5, when I use this formula, I get 5.523. For 50, some of you have calculated, that is Y is 5.5397. Okay, so that is the right answer. So most of you got this right, and the fitting also right. So if you look at now, okay, so now comes the most interesting question. Okay, so let's go look at, even with fitting, the value is off, right? Okay, so then comes the question as to why we should use fitting instead of using linear interpolation. Okay, so whether I use fitting or linear interpolation, in both cases I am getting values which are away from what is experimentally determined. Now the question is, why should I do fitting at all? Why can't I do linear interpolation? So So if some of you would like to answer this question, if you raise your hand or if you put a note in the chat, I will give you video so you can try to answer this question. So what is it that we did? We had some data. We took some 2 data points. We tried to calculate lattice parameter by doing linear interpolation. And we found that that linear interpolation might not be correct, because when for a known value you try to do interpolation, it gives you values which are off. Then we said, okay, this is because of experimental errors, so let us correct the experimental errors. So we did the correction for the experimental errors by doing least square fit, and then also we got values which are away from what is experimentally data. Okay. So now the question comes whether we should take the effort of doing all this fitting at all, whether we can directly do interpolation for all problems and forget fitting. Okay. So if you want to answer, please let me know so you can answer. So all of us will hear the answer, and then we can have a small discussion about this before we move on to the next topic. And in the meanwhile, I mean, if you have any other question or any other point you wish to discuss, or whether you have any other clarification, we can do that, then we can proceed. Okay. Anybody wants to answer the first question? Is fitting preferred at all? Okay. If you don't want to answer, if you want to just write the answer in the chat, that is also fine. I'll read out your answer and then we can discuss. Yeah, any center wishes to answer? You can hand raise, and if you select the option hand raise, then I will allow you to. Yeah, there is some.
To minimize the XA and Y distance, we are using fitting. Instead of interpolation, we are using fitting to minimize the XA and Y distance.
Right, we are minimizing errors. So fitting should be preferred?
Yes.
Because we are minimizing errors?
Yes.
Yes, very good answer. So because when we are doing fitting, we are minimizing errors. Even if it is a straight line fit, we should use fitting. Sometimes, for example, it might not be straight line fit. It might be quadratic fit, for example. Okay. So then what happens? In that case also, you can interpolate, but linear interpolation will give really bad values. So if you know some type of functional form exists, we should always prefer, because fitting is slightly more accurate calculation in the sense that it tries to get rid of all the experimental errors or minimizes the effects of experimental errors. So it has to be preferred. There are ways of incorporating information about the error in the data itself and doing a better fitting. So it is preferred to do fitting. So very good. So I am happy. Is there any other question or query that anybody has? Or comments? Are we going at the right speed? Anybody wants to say anything? If not, I'll move to the next question. Okay, if you have, please raise your hand. So we can go to the next question. So if you want to fit a higher order polynomial, say quadratic polynomial, suppose I want to fit a0 plus a1x plus a2x squared. Okay, how do we do that? So that is a question, so which we will answer at some point during the course, but you can think about it. We are not going to answer this question today, so you can think about how to do that. And sometimes you might fit, but that might not be a proper polynomial. Like for example, y equal to ax plus bx squared. What does that mean? That there is no constant, there is no c. Okay, sometimes, for example, you might be fitting for a stress strain curve. Okay, then when the stress is 0, the strain should be 0, or when the strain is 0, stress should be 0. So it is fit to y equal to mx and not y equal to mx plus c. In those cases, how do you do fitting? If you have any questions, even during the session, please don't hesitate to stop me, and then we can have a discussion before we proceed further. Okay. So I'm going to go to so this is the third topic. So we had some preliminaries, then we discussed about fitting, interpolation, extrapolation and things like that. So in this, I'm going to talk about how do you deal with numerical data. Okay? We know how to do differentiation. If I tell f of x is equal to x squared, you know how to take df by dx. Okay? But suppose I tell you that f of x is these numbers for these x values, how do I differentiate this data? This differentiation is known as numerical differentiation. So you are taking a set of numbers and you are doing differentiation. Similarly, if I tell you that f of x is equal to x squared, integral x squared dx, you know how to calculate. But if suppose I told you that these are the f of x values for these x values, how do you integrate this data? So that is known as numerical integration. So we are going to do these two topics today, and these also form the basis for some of the other algorithms that we will use later, because we don't just integrate functions, we take differential equations, we integrate them to obtain solutions. Okay, so the numerical differentiation ideas will also be used in integrating differential equations. Okay, so it becomes very important. So because of which, and approximating derivatives using differentiation, numerical differentiation is an important topic and is widely used. So we will also discuss that later. So this forms basically the basis for those computations. So we know how to calculate derivative of a function or integrate a given function as long as it's a continuous function. Okay. What we are trying to do is to carry out the same operations on discrete data. Okay. While we do it on discrete data, it is called numerical differentiation and numerical integration. So there are difference formulas, okay, and the first one is known as the forward difference formula, and the forward difference formula actually uses the Taylor series expansion. Okay, so we have seen the Taylor series expansion. So let us take a look at the Taylor series expansion for f of x plus h. Okay, so that had several terms. Okay, it had f of x plus h times f prime of x plus h squared by 2 factorial f double prime of x and so on. So let me stop the computation with the first term. Okay. So what is the error in such termination? That will be of the order of h squared, because that is the kind of term that I have neglected. Now, so what do I have? Now I have f of x plus h is approximately equal to f of x plus f prime of x times h. So I can take f of x to the left hand side, I can divide by h, then I get an expression for f prime. What is f prime? It is df by dx. So now I have an expression for df by dx, which is in terms of the function values given at points x and x plus h, and the distance between x and x plus h is basically h. So you divide by it, you get the difference formula. This is known as the forward difference formula, and because there is a division by h, the termination error, even though is of the order of h squared, the error in the derivative is of the order of h itself. So because it will be, the h squared term will be divided by another h, so it will lead to an error of the order of h itself. So when h is less than 1, you know, h squared will be much smaller, but h will be of the order of whatever number you have. Okay, so this is known as the forward difference formula. Okay, you can use the Taylor series expansion for f of x minus h and derive what is known as backward difference formula. Okay, so what does the backward difference formula give? So it is exactly like forward difference formula, except that it says f of x minus f of x minus h divided by h is basically f prime. Okay, so that is backward difference formula, and you can take an average of the both, that is combine forward and backward difference formula, and then you get what is known as central difference formula. What does central difference formula tell? Central difference formula says f of x plus h minus f of x minus h divided by 2h is equal to f prime. So there are many different formulas that are available for calculating the numerical derivative or for carrying out numerical differentiation. Okay. Now, why is this process okay, so we know that the error that you would get in forward or backward difference formula is of the order of h, but what happens if you do central difference? So for that, let us do the computation. Okay, so let me take the okay, so let me take the forward difference formula. It said that f of x plus h minus f of x divided by h. Okay, so this is forward difference formula. Now backward difference formula said f of x minus f of x minus h divided by h is backward difference formula. Now what is central difference formula? Central difference formula says that it is f of x plus h minus f of x minus h divided by 2h. Okay, so this is central difference formula. So what happens when we are doing the central difference formula? You can see this is this plus this divided by 2. Okay, central difference formula is obtained by taking forward difference formula plus backward difference formula divided by 2. So that is why this and this get cancelled, this minus this divided by 2, so that is 2h. So that is how we have got it. Now because we have this forward and backward difference formulas, then the error, that the term that is there, that will have different signs. So when you take the average for the central difference formula, that first term in the error will go away, so the error will become much smaller in the central difference formula. So that is why central difference formula is sometimes preferred, because even though error is of the order of h here, right? So if you calculate error that is of the order of h here, it becomes order of h squared in the central difference formula. Okay, so it's very important to note that error becomes very small when you use central difference formula. So when you want more accurate evaluation of the differentiation, you use central difference formula. Okay, so let's go back to the slides. So error becomes much less if you use central difference formula. So here I have stress strain data. This is data developed at our FIST mechanical test facility that we have in our department, and this is courtesy due to one of my colleagues, Professor Preeta Pant. I don't remember whether this data is for aluminum or for brass. It's one of those metal or alloy. So the experimental data is given as stress versus strain. Okay, so for this stress this much is the strain, for this stress this much is the strain, and so on and so forth. So if you plot, this is where using a program like GNU Octave becomes very important. So you can plot and you get some curve like this. All of you must have seen curves like this. So this is the stress strain curve. So there is a linear region. Okay, so that linear region, if you take the slope of that linear region, that gives you the Young's modulus for the system. And then there is a yield point at which the linearity breaks down and some non-linearity starts. And it's very difficult to find out the yield point. So typically one takes 0.1 or 0.2% proof stress. That is, you go in strain point 2, draw a line which is parallel to this straight line and find out where it cuts this curve, and that is your yield strength. And then there is UTS, and then there is a point up to which so that there is hardening, and then there is failure. So the area under this entire curve is known as toughness, and the area under the linear part of the curve is known as resilience. So you can see why numerical differentiation and integration becomes important if you are having. So all that you have is data which is discrete. You have some points, strains, and some stresses for that. Now you want to get the slope for the linear part, and if you get that, that will tell you what is the Young's modulus of the material. If you integrate the linear part of the curve, because the area under the curve is basically integration of this function, then you will get resilience. If you integrate this entire area under the curve, then you will get toughness. Okay, ductility is the point up to which it fails, and the toughness is the area under the curve. So calculating toughness, for example, would involve carrying out a numerical integration. So it's very useful if you get experimental data like this. Then by performing these operations to get the information on this system, what is its Young's modulus, what is its toughness, what is its yield strength, and so on and so forth. Okay, so if for example you can fit a straight line to the linear region, then you can take the point to proof stress and draw a line, and then you can find out where the curve intercepts. But because this is discrete data, then you also need a fit for this part and where the straight line will intersect that nonlinear part, and then you can get. But if your data is closely spaced, of course you can also do a linear interpolation and you will not accumulate lots of errors. Okay. However nonlinear the curve be, if you go to very small ranges of strain, it would still look linear. So you can approximate a nonlinear curve by small linear regions. Okay, so it's possible to do. So there are many different ways of doing it, but the point is that we need to calculate or carry out numerical integration and differentiation many times, and that is very important. Okay, so we have a stress strain curve. Okay, so the yield stress of the given material, that is the yield point. Okay, I should be careful about it. It's a yield point. So that seems to be somewhere around 130 MPa. Okay, so about 130 MPa, I can assume that it deviates from linearity. So if so, if I can go back to the data and find out where the stress has become 130. Okay, so that is like the first 1, 2, 3, 4, 5, 6, 7, 8 data points. Okay, if I take the first 8 data points and calculate the slope of the curve using those data points, then that will give me the Young's modulus of the system. Okay, so the first 8 data points corresponds to the linear or elastic region. Okay, so because about 130 or so it is becoming nonlinear, so I'm going to leave out this data. So I'm going to look at this first 8 data points. Okay, so if I take the first 8 points and calculate the derivative, okay, how do I do? I calculate the consecutive points and I use the difference formula. So what does the difference formula say? 6.6 minus 4.08 divided by 0.01, right? So how much is that? So let us do the calculation. Okay, so I have 6.6 minus 4.08 divided by 0.02 minus 0.01, that is what? Okay. Okay, so I have given okay. So thanks Shobhan. Shobhan is pointing out that this is in MPa and this is in percentage. So this is 10 power 6 and this is percentage, means it has to be multiplied by 100, right? Right, so this will be 10 power 6, that is okay. And so this is 0.02%, that means what? It is 2. So this is 10 to the power 2 minus 2. So that will become 10 power 8, 10 power 8. Okay. Okay. So it's always good to have Shobhan with me. So Shobhan points out that this is MPa, so 10 power 6 is there, and this is in percentage, so 10 power minus 2 is there. So 10 power minus 2 goes there, so it becomes 10 power 8.01. So if I have this, okay, so this is 0.01, this is 2.52, so multiply by 100 on both sides, so you'll get 252 into 10 power 8, so that will be 25.2 into 10 power 9, that is 25.2 GPa. Okay, so that is what the first value. We can use the next one, for example, one is 10.01 minus 6.6 and divided by 0.03 minus 0.02. So again, so it's 10.01, 6.6, okay. So that will become 34.1 GPa and so on. So you can do this computation. Okay. So let's go back to the table and see. So if I consider the consecutive points, I get the d sigma by d epsilon in GPa. So if I consider the first 2 points, I get 25 points. If I consider the next 2 points, 10.01 and 6.6, I get 34.1. If I get 15.64 and 10.01, I get 56.2. Okay. So, and then I get 64 and then I get to 82 and then I get 64 and then I get 65. So some numbers are around 64, 65. So this is probably data for aluminum, and some numbers are off because I'm suddenly getting some 82, and some numbers are also really small. I mean, I'm getting 25 and 34. Okay. So if you calculate the elastic moduli by looking at data, okay, the errors in the data will have a huge say in what is the modulus that you are calculating. So in these cases, the way to do the computation is by changing the window that you are using to calculate the modulus, and also sliding that window. Okay, so doing that actually gets rid of lots of numerical errors that you will generate in the process. Okay, so but see, if you look at the figure, it looks nicely linear. Okay, and the modulus is not. That is because in the linear region, okay, you have the entire curve. So you have a very small region which is linear. So in that region it looks linear, but if you go look quite closely, you will see that it is not approximated by straight lines of the same slope. So there is some slight variation, which is what shows up when you calculate the numerical differentiation. Okay. So if suppose you calculate the elastic modulus by taking the first and last point. Okay. So take the last point, take the first point, take the difference, and take this strain difference and calculate the modulus, and in chat let me know what is the modulus that you are getting. Okay, please do this computation. So let me do it. Okay, so please do the computation and tell me what the number is. I am going to do the computation myself, and we will compare the numbers. Okay. It is the same formula. So 111.88 minus 4.08, and the strain goes from 0.18 minus 0.01. Okay. So there is a 10 power 8 that is there because the denominator has percentage and numerator has MPa. So if you do that, there is a 10 power 8. So please remember that. Otherwise, like I was wondering what was happening earlier, you will also have difficulty in finding the right unit. Okay, so that do, and please tell me what is the number that you get. Okay, so okay, 63.4, 63.411. Yeah. Okay, so Shobhan is also getting 63.411. So you can see that the moment you took a slightly larger range, the number is, and it is quite close to what we listed here, 64, 64, 65, 63. So I think aluminum has the modulus in this range. So this looks like the right number. Okay, 69. Okay, so I'm also hearing the aluminum is 69. Okay, so I understand aluminum is 69. So this data is quite close to that value. Okay, so several people got 63.4 and odd. Okay, so very good. So we calculate, if you calculate first and last point, you get. Okay, so it is also possible to take a sliding window of larger size, say 2 to 3 points. Okay, and of course the data also tells you that maybe the initial adjustments are the reason. So you can sometimes, discard these 3 points. So you will take data somewhere from the middle to the last. You can look at the difference and calculate, or you can take say 4 to 15 and then 6.6 to 22, 10 to 46 and 15 to 72 and 22 to 111 and calculate the modulus. So there are many different ways of doing it, and if you have data which is not well behaved or which is error prone and things like that, so it becomes very sensitive to how you choose the window over which, if it was actually a proper straight line, mathematical straight line, then it doesn't matter whether you take the slope over 4 points or over the entire region. But when you have numerical data which is prone to errors because it is experimental data, then you have to be careful about how you choose the data and how you do the computation. Okay, so that is the point behind this exercise of doing the calculation. Okay, very good. So this is something that you should think about. Okay, you have the data, so you can do this exercise. You can slide up and down and see what happens to the modulus that you calculate. Okay, very good. So okay, so there is a small error in this slide. I'm going to correct it. I will correct it later, and I'll ask the corrected version to be posted. So it is resilience and toughness. See, ductility is the point to which plastic deformation takes place before it fails. Toughness is basically the area under the stress strain curve. So okay, so this is given wrongly both in my notes and in my slides. I will correct it. So area under the elastic part is basically the resilience, and area under the stress strain curve is the toughness. Okay, so both these actually require numerical integration. How do we do numerical integration? Okay, so the numerical integration for unevenly spaced data is calculated using the so-called trapezoidal rule. Okay, so if you want to integrate f dx, then it is nothing but sum. Okay, so you have different points I and I plus 1 and etc. So you sum for all I, fi plus fi plus 1 by 2. So that is, you take the function value for the ith point, I plus 1 point, you take the average of it, multiply by the xi plus 1 minus xi. Okay, so if they are evenly spaced, then xi plus 1 minus xi is the same for everything, so that becomes h. Then you can pull that h out, and if you have some n data points, and it becomes just nh. Okay, so this is the difference between evenly spaced data and unevenly spaced data. Most of the experimental data is unevenly spaced, so we have to calculate integration using unevenly spaced data, and this is the formula that tells you how to do integration for unevenly spaced data. There is a wonderful textbook by Gerald and Wheatley called Applied Numerical Analysis. This formula is taken from Gerald and Wheatley, so I strongly recommend. Most of you would have seen Crazy, okay? But I also strongly recommend you to take a look at Gerald and Wheatley from your library. If it is not there, you should probably recommend that it be bought in your library. It's a great book to have. And this formula is from Gerald and Wheatley that I have taken. Okay, so now let's go back to the data that we have. Let us calculate resilience. So if I want to calculate resilience, what is the formula? The formula is given in the bottom. It is summation I fi plus fi plus 1 by 2 multiplied by xi plus 1 minus xi. Okay, so this is xi plus 1, this is xi, and this is fi plus 1, this is fi. So you keep doing that for every point, and then you sum them all up, you get resilience. Okay, so I want you to now calculate the resilience by doing the numerical integration. Okay, that is the first step. Can you please do and tell me the number? Okay, so this is 1, 2, 3, 4, 5, 6, 7. 7 additions, 7 subtractions, 7 multiplications, and the resultant number, all of them have to be added. So there are another 7 additions. Okay, so that is the number of operations. So it's slightly involved. It might take a couple of minutes, but I want you to do, and then some of you might know that if you know the linear region, so that is described as sigma equal to Young's modulus times epsilon, the strain. There is an analytical formula which involves the total elastic strain and the Young's modulus, and we have already calculated the Young's modulus to be 63 or something for this system. So you can do an independent calculation of resilience from that formula, and you have this numerical integration, so we can compare both and see how it fares. Okay, so that will be an interesting exercise for us to do. So please do the computation, and when you get the results, tell me through the chat. Okay. Very happy that we have been getting lots of answers till now. At least every time I had minimum 2 to 3 people getting the answers right. So this is the last computation for the day. Somebody has reported 0.0534. Okay. Okay. Is this resilience? Okay, it looks too small a number. Okay, total strain. Oh, okay, so there is also strain percentage. So point. So can you tell what is the unit? Please report the number, and you also tell me what is the unit in which you are calculating it. Okay. So approximately this is like 6 minus 4 is like 2, and this is like 4, and this is like 5, this is like 7, this is like 24, and so on, and they are multiplied by 1 into 10 power minus 4 here, 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 3 into 10 power minus 4, and 4 into 10 power minus 3, and 6 into 10 power minus 3. So that is the kind of numbers that are multiplying. So it is possible that it is small number, and there is a verification. So you have 63.43 for the modulus, half times that times epsilon squared, that is 0.18 into 10 power minus 2 whole squared, is basically the resilience. That is what the numerical formula, I mean the analytical formula derived would be. So we can compare. Okay. Yeah, so I have a value of 9.3995 into 10 power 4 in, yeah, somebody got 9.399. Okay, very good. So if you compare with the sigma y squared by 2E, where E is the elastic modulus and sigma y is the yield strength, which is we calculated to be 130 MPa or so. So you can calculate and see if it compares well. Okay. So very good. So that brings us towards the end of this session. So I have one more question. Like I said, this is not ductility, this is toughness. So you have this stress strain data, and you can calculate toughness, and you can find out how the numerical integration works. So to summarize, we have found out that numerical calculations, when they are done, you have to be careful about errors and how the approximations are done. And the Taylor series expansion is another basic thing that you need to remember for doing lots of these computations. Then we looked at fitting, and we looked at interpolation and extrapolation, and fitting is preferred because it tries to minimize the experimental errors that are generated when you calculate experimental, when you obtain experimental data. Then we looked at how to do numerical differentiation and numerical integration. So that brings us to the end of this first session. So next session we will spend lots of time doing linear algebra, matrix calculations, eigenvalues, eigenvectors, solving simultaneous linear equations and so on and so forth. Again, the examples that I will choose will be from material science and engineering, some problems that will be of use to people who work with material science and metallurgy problems. So for today I'm going to stop here. If you have any questions or comments, I will take, otherwise we will end the session. If you have something to say, some comment, or if you want to give some suggestions, please raise your hand and we can say, or please type it in for me in your chat window. Any questions? Any comments? For the next two sessions also, I request you to please bring a calculator. We will try to do as many of these computations as possible as the lecture progresses, so that A, you will not be bored, and B, it will also help you see what is meant by a algorithm or calculation. Great. So if there are no questions, then I'm going to stop the session now. So thank you very much.